Okay, class. Someone asked in class the other day. They asked me to derive the formula, like why that dot product u dot v equals length of u times length of v cosine of theta. Like, where does this come from? So I'm going to do that in this video. We start with the law of cosines. And if you can't remember the law of cosines, it's a generalization of the Pythagorean theorem. Notice if you cover out this much, then you get a squared plus b squared equals c squared, which is the relationship of lengths in a right triangle. And when theta is 90, then cosine of 0 is 0. So, but this allows us to use a similar relationship, and when we don't have 90-degree angle, it works for any angle. So, so we're going to start with this, but what we have to do is translate these lengths into language of vectors. So, so imagine we had points here. Oops. If we had points here or coordinates here, we could subtract one vertex from the other vertex to get a vector, and we'll call this vector u, and we'll call this vector v. Okay, so that means a, which is the distance of that side, is the length of u, and b is the length of v. And now we can start rewriting that at least a little bit. So on the right hand side, we'll have the length of u squared plus the length of v squared minus 2 times the length of u times the length of v cosine of theta. The right hand side, so we need c in terms of u and v. To get this vector, we can do subtraction. We can do u minus v or v minus u. That'll get us a vector that goes from the head of one to the head of the other. Since we're squaring it, it doesn't matter which one we do, so we can just take u minus v absolute value, not absolute value, norm squared. So, so now we have everything in terms of u and v. And I'm going to go one step further. You can go from here, and the book does. In this section, it goes to here, and it just works with the properties of dot products and norms, and it'll do it. I'm going to go one step further, and I'm going to write out what this, what u is in terms of coordinates. So we're going to let u equal u1, u2, u3, dot, 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 down to un. So this isn't just in the plane. We're doing this. This is supposed to work for vectors in Rn. So however many dimensions we have. So v1, v2, dot, 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 down to vn. So, and so I'm going to, this might take some space, but I'm going to replace all of these u's and v's and these squared norms. I'm going to put them in as the vectors. So with these coordinates. So what does that mean? Well, if we have the length of u, that's the square root of u1 squared plus u2 squared up to un squared. So everywhere there's one of those, I've got to replace it with this. So u minus v norm squared is going to be u1 minus v1 squared plus u2 minus v2 squared dot 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 un minus vn squared. If we didn't have the 2 here, we'd have to do the square root, but it's the square root squared, so those cancel out. So now we have u1 squared plus u2 squared dot 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 un squared plus v1 squared plus v2 squared dot 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 vn squared minus, here we do get some square roots, 2 the square root of u1 squared plus u2 squared plus dot 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 un squared. You can see why mathematicians like to create notations to keep things small. So isn't this line much better than the line below? And then we have one more square root here. v1 squared plus v2 squared dot 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 vn squared times the cosine of theta. Barely had enough room, okay, to put that on there. So let's chop that out. Okay. Well, let's expand this side. So for each of these, we're going to get a u1 squared minus 2u1 v1 minus or plus v1 squared. Plus, I'm not going to do that one. We'll just do the dot dot dot. We'll jump to the nth one. un squared minus 2u1 v1 plus vn squared equals, and notice I'm going to save myself some time because that's just going to come down, this is just going to come down, but also I have u1 to un squared over here, but I also have them over here. The first of the three terms of every one of those is just the u1 squared, u2 squared, u sub 3 squared, all the way up to un squared. So those actually cancel out. Oops. These will cancel out with all of those first one terms. And then similar with the last terms, these vi to the vi squareds, they'll cancel out with the third terms of each of those expanded quadratics. And so all I have left over here are these 2u1 v1 plus minus 2u2 v2 down to minus 2u, oh, those should be n's, un vn. Okay, so that's on that side. Over here, we can, what do we want to do? Well, we could put those underneath the square root. I don't know if that helps us very much, but we're trying to solve for cosine of theta. We could try doing that. We also have a minus 2 over here, and we also have minus 2's in front of all those. So let's divide out by the minus 2's on both sides. And let's write out what we have left. So we have u1 v1 plus u2 v2 plus u3 v3 dot 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 un vn equals the square root of u1 squared plus u2 squared dot 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 un squared times the square root of v1 squared plus v2 squared dot 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 vn squared cosine of theta. Well, look at this side. What do we have over here? What does that look like? Well, you multiplied pairs and you added them up. That is dot product. So that is just the vector u dot the vector v. Or we could write it out as u1, u2 dot 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 un dot v1, v2 dot 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 vn equals, and here we could go back. This is just the length of u. So we could go, okay, length of u, that's where we started with anyway up there. And this is the length of v, and cosine of theta. So we get the dot product of the u and v vectors equals the length of u times the length of v times cosine of theta. And we could go one step further if you wanted. We could do u dot v. Should have put my vector markers on all those. And divide by the length of u divided by the length of v. equals the cosine of theta. So all this starts with the law of cosines. Translates the length in terms of vectors. So we put it in terms of language, vector language, and then we just do substitutions, expand out. You don't have to expand out. The book does the non-expanding one, but if you expand out, you see this operation here. Like you get to see I'm multiplying u1 times v1 and u2 times v2, and you're just pairing them up, multiplying them, and then adding them up. So this is the dot product. So that's where it shows up. Okay, hope you enjoyed that. Hope that helps. Thanks, and bye-bye.